Okay, let's work problem number 49. I'll read the problem. It says, use Newton's version of Kepler's third law to find the mass of the Earth. The moon is 3.9 times 10 to the 8 meters away from the Earth, and the moon is a period of 27.33 days. And then compare this value to the mass found in problem 39. So here's basically what you've got. Here's the Earth. Here's the moon. The moon moves in a circle around the Earth with a period of 27.33 days. We want to know what is the mass of the Earth. And I'm going to solve this. I'm not going to use Kepler's law or whatever. I'm just going to use the orbital velocity equation. And it's really the same thing. Okay? The orbital velocity of the moon around the Earth is equal to the square root of big G times the mass of the Earth over the distance r. Right? That's the orbital velocity equation. And so this is what's being orbited. This big M right here would be the mass of the Earth because the moon is orbiting the Earth. And then this r is the distance from the center of the Earth to the center of the moon. And that's what they gave you here. You didn't really need to add the radii of the Earth or the moon to that value. Well, we need to figure out, so we can solve for the mass of the Earth, square both sides, so that's the orbital velocity squared, times r divided by g. Okay? Can I explain how I just did this? Okay. Let's do every algebra step.
Thank you.
Square both sides. Multiply both sides by r. Divide both sides by g. Mass of the Earth equals the orbital velocity squared times r over g. Now, do you believe me? Okay. All right. So, now I know this is given and this is given, but I need to know what the orbital velocity is. Well, the orbital velocity is just equal to the distance divided by the time. So it's the distance, it's 2 pi r over the period. Well, the period, though, has to be in seconds. So let's change that. The period is equal to 27.33 days. Put that over 1. 1 day is 24 hours. Now, 1 hour is 60 minutes, and 1 minute is 60 seconds. 60 times 60 is 3,600. Whoop. Thank you. 3,600 seconds. Okay? Zoom out a little bit. Did anybody do this calculation? What'd you get? Yeah, let me check that because I couldn't hear you anyway. All right. Yeah, 27.33 times 24 times 3,600, and you get 2.361. I'll carry and 1, 2, 3, 4, 5, 6 times 10 to the 6 seconds. Is that right? So think about this. A month, well, this is a little bit less than a month. So a month is about 2.5 million seconds. Let's think about that. That's kind of a cool thing to know, I think. All right. So anyway, so now we can use that up here. That's 2 times pi times, stop dropping stuff, 3.9 times 10 to the 8 meters over 2.361 times 10 to the 6 seconds. So what can I do with this? Can I do that with this calculator? Oh, I don't like this calculator. I'll just start over. So 2 times 3.1415 times 3.9 times 10 to the 8 divided by 2.361 times 10 to the 6 equals, and we get 1,038, if I round it up, meters per second. Agree with that? Yeah. So now I can plug that in here. And there's more than one way to do this. So this is going to be 1,038 meters per second. I'm going to square that. I'm going to multiply it by the radius, which is 3.9 times 10 to the 8 meters. And I'm going to divide that by g, which is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And wait a minute, something is goofy here. Oh, okay, no, it's in the Newton. It's all good. So I'm going to take this and I'm going to square it. And then I'm going to multiply that times 3.9 times 10 to the 8. And then I'm going to divide that by 6.67 times 10 to the negative 11. And I get 6.3 times 10 to the 24 kilograms. And that's our answer.
Sweet.
Okay. Now, how does that compare? Well, the actual mass of the Earth, if you look it up in the table, I think it's 5.97 times 10 to the 24. This is 6.3. So it's pretty close. You know, it's now why is it off at all? Because the moon doesn't move in a perfect circle around the Earth. It moves in an ellipse, and it doesn't move around the center of the Earth. It moves around the center of mass of the Earth-Moon system. So there's little things in there that are going to make this be a little bit wrong, but it's pretty close to being correct. And here's something really interesting about this. This is how we figure out what the mass of black holes are. We've observed, well, you can't see a black hole, right? It doesn't give off any light. And that's all telescopes can do, is look at light of various frequencies. Some frequencies are not visible to our eye, but still. But here's what we can do. Let's say you see some empty space here. Like here's the blackness of outer space. But you see a star. And that star is moving in a circle around empty space. And if you can estimate the radius of that, and we can do that, if you know how far away the star is, and you can see what this, you know, you can figure out what r is. And if you measure how much time it takes that star to go around this empty space, you can figure out what the mass is of that missing object. And that's how we figure out the mass of black holes. If there's a black hole out in space all by itself with nothing orbiting it, it's really hard to tell. I mean, you really have no evidence of anything being there. But if a lot of black holes are part of binary star systems. So, I mean, there's more than one object, and if you have a star that's orbiting a black hole and you make an estimate of its radius and you make an estimate of the period, you go through exactly these calculations that I just did for the Earth and Moon instead, and out comes the mass of your black hole. Yes?
Do black holes like just suck things in? Like, are they just like...
Well, the question is, do black holes just suck everything in? Well, they can, if the trajectory is just right. I mean, if, let's say there's a some kind of, here's the event horizon. If something is just moving right towards it, yeah, it'll just be pulled in. But it's just a gravity field. A black hole is just a gravity field. And, I mean, the Earth forms a gravity field, right? And things orbit the Earth. Does the Earth suck everything in? It's not sucking the moon in. But the moon is in orbit. So things can be in orbit around a black hole, just as they're in orbit around a planet or a star. Or, in fact, at the center of our galaxy is a supermassive black hole. Billions of our sun's mass concentrated at one point in space in a gigantic event horizon, and it's not sucking us in. Why? Because we're moving with respect to it. You have to fall into it, and we're falling around it. Never to fall all the way in.
So where does it go if it goes in?
Well, okay, so the question is, what happens if something gets sucked into a black hole? We don't know.
We should send it.
I mean, here's the thing. We have mathematical speculations, and what we think is happening is that you're having a tear in the fabric of space. The gravitational field becomes infinite, and it's like you have a point in space with infinite density. And it's, but what actually happens to the matter? As far as I know, we don't really understand that. And it's really going to be hard because there's no way for us to do an experiment, because there's no way to go into a black hole, do an experiment, and then get out of it to see the results. In other words, it's a region. They have this thing called the event horizon, and you can't get inside that event horizon and get any information out of it. It's lost. It's like a region of space that's lost to our universe. I mean, it's there, but if you go in there, you can't get out. And you can't even get information out. If you were in here and you had a walkie-talkie, the radio waves wouldn't be able to get out.
How do you know that for a fact?
Because Carl Sagan told me. Any other? Okay. Oh, that's it. That is all.